Greetings! This is a primer video for a series called Piecemeal, where I do bite-sized musical tours of classical music for the lay audience. The goal today is to get a basic enough understanding of a compositional approach called Dodecaphonic music, so that I can then talk about composers like Schoenberg, Webern, Dalla and others. In order to do that, I'll have to establish some music theory vocab, and I don't want to do definitions in the actual analysis video. So here's this one. To begin, we have pitches and notes. Pitch is a sustained, discrete tone we can hear. One way to measure pitches is by how fast the wave comprising them is vibrating. Notes are the names we give to each discrete pitch. In Western music theory, we currently use the first 7 letters of the Latin alphabet, A, B, C, D, E, F, and G, and by somewhat agreed upon convention, the so-called concert A is usually established somewhere around 440 vibrations per second. It sounds like this on a piano. Next, an interval is the bucket term we use for describing the relationship between any two pitches. These pitches can be played in sequence for a melodic interval, or they can be played simultaneously for a harmonic interval. There are a variety of ways to describe this relationship. In a mathematical way, intervals are actually ratios. If two instruments are playing the exact same pitch, they are vibrating at a 1-to-1 ratio, and we call that interval a unison. If two instruments are playing pitches at a 2-to-1 ratio, we call that interval an octave. Because of how human brains work, we have a sensation called octave equivalence. That means that our perception of octaves is very close to our perception of unisons. Octaves sound like unisons, just fatter? Yeah, sure. We also have extremely similar perceptions of any interval, regardless of which pitches we use. As long as the ratio is kept the same, we perceive the same interval. It's a little bit like looking at two different but similar triangles. We can clearly see they are the same triangle, even if one is smaller than the other. Here are a few different octaves for demonstration. Because of octave equivalence, when we play through all the letters in sequence from A to G, the next letter after G, an octave above A, is another A. The letters continue to cycle in this way until pain or inaudibility. Normally, we don't use ratios to talk about intervals. We instead use the note letters as a kind of musical ruler. Comparing the exact same letter, a unison, is 1. Comparing any letter to an adjacent letter is called a second. We bump into a problem, however, which might be audible when I play all the letters from A to A. Not all of the changes sound the same. If I play A to B, and then B to C, you can probably hear those changes are perceptibly different. In order to account for that difference, we give those intervallic seconds an extra descriptor. The sound change we hear from A to B is called a major second, and the sound change from B to C is a minor second. In this case, minor and major just mean small and big. If you worked out the math, the ratio for a minor second is a little smaller than that of a major second. We're getting closer to the goal of this primer now. If you're thinking to yourself, wait, if minor seconds are smaller than major seconds, does that mean there are more possible minor seconds than the letters account for? Then congratulations, you would be correct. To help us talk about and notate the other possible minor seconds, we use the symbols and terms sharps and flats. Sharps and flats are descriptors added to the letters. We might say F sharp or B flat. Sharps refer us to the pitch a half step above the given letter. Here's F and F sharp for comparison. Flats refer us to the pitch a half step below the given letter. Here's F and F flat. Okay, now some instruments have fixed note production. Think of pianos and guitars. Because of how the math of tuning works, trying to tune these fixed positions beyond a single octave gets kind of wonky. I don't want to get into that. I'm only talking about it to bring up the solution that has long been settled upon for these instruments, a method of tuning called equal temperament. The way it works is all the minor seconds are tuned to the same ratio. This means every change between every possible minor second across the whole instrument sounds the same. If we put all of these minor seconds in sequence, we get what we call a chromatic scale. It sounds like this. With all of that established, we can now talk about this guy, Arnold Schoenberg. For a bunch of historical and personal reasons I don't want to get into for a primer, Schoenberg created I don't want to call it a system, he created a paradigm. He took the chromatic scale and said, hey, if I arrange these 12 notes in interesting ways, I can use that unique sequence of intervals to write music. These unique sequences are called tone rows. Tone row might sound like this, or like this, or like this. Schoenberg himself thought of these tone rows as like Ur motifs, a single unifying melody that underpinned an entire composition. For listening purposes, I'm not sure how helpful that is, especially for untrained audiences. The point is, the most important composition principle he established was that the pitches themselves be presented in the same order. That is, if the tone row starts with the notes A, B, G sharp, and C, then a composer should think really hard about creating a musical idea that goes A, B, D, G sharp. It would be possible within this paradigm, but that out of sequence D would ideally come from another form of the row. What other forms are possible? Well, a composer could take the row and play it backwards. This would be called a retrograde of the row. Composer could also take the sequence of intervals and flip them upside down. The interval type is kept the same, but if it went up in the primary form, it would go down, and vice versa. This is called an inversion. Inversions can also be presented in reverse for a form called, somewhat cheekily, a retrograde inversion. Lastly, any of these interval sequences can begin from any of the 12 notes of the chromatic scale for what's called a transposition. To help theorists and composers keep track of all these possibilities, this gnomish looking fella, Milton Babbitt, is credited with inventing the 12-tone matrix. Would love to be corrected if this is wrong. The matrix looks like this, and is absolutely not something most listeners need to have to appreciate music written in this paradigm. In fact, there are some challenges which come up when considering how 12-tone music is analyzed versus how it is actually heard. Despite the restriction on presenting the notes of the tone row in sequence, a composer has great flexibility in choosing how many notes from the row are used to make a chord, how those notes might be stacked on top of one another, how many times a particular note is repeated, when and which new row forms are introduced, and on and on and on. This can result in what I'll call emergent materials, musical ideas which aren't necessarily present in the row itself, but are nevertheless an audible structure based on how the fundamental building blocks were arranged. For me, these emergent materials are often the more interesting part of 12-tone composition. They are certainly going to be the more salient feature for my piecemeal analyses. So there we have it, a quick and dirty rundown on dodecaphonic composition. I hope this was interesting or at least edifying. It will be helpful as a reference when I discuss 12-tone composers for sure. Thanks for stepping in.